And now we're live. Ladies and gentlemen, good morning, good afternoon, and good evening from all of you who visit us from everywhere in the world. This is another day, another sunny day here in Venezuela. Luis here. Nice to see you again, helping with this great series of knowledge from Populi. And today we have a very, all guests are specials, but I'm not gonna lie to you. This time I'm super more even more excited because Harshit, who is here in the camera, is a personal friend. He's one of the coolest guys ever. If you ever have the chance to hang out with him, you're gonna be with a smile in your face from start to finish, and you will even wish there's no finish, just like me. And yeah, so today we have a very interesting topic, guys, which is something that you love. We know that you love everything related to artificial intelligence, and Harsh is going to teach us the nitty gritty details of how it works and how why it's important and how it has been evolving over the years. But first of all, hi, I like to see where you guys come from as always. We have Irene from Kenya. Hello, Erin, again. Abdullahi, Rada. Hey, Rada, you don't cheat today, okay? Rocio from Spain. From which part of Spain, Rocio? So curious to know. Was in there a couple of years back. We have Jesse. Where's Jesse from? We can have a special treat today if someone guess where Jesse's comes from. Yeah, and yes, as it says in there, this is the last episode, so I hope that you guys enjoy it, and I'm sure you will enjoy it with our special guest that we have, which is Harshit. Shri Saya, nice to see you from Hyderabad. Harsh is from India, by the way, born and raised in India. He will know many of the places that you guys were writing here, like Hyderabad. I think we had last time someone from Shimla. I was so happy to see that. And Valencia. Nice, nice Brazil. I have a cousin who lives in there. And oh, Morocco. That's so cool. Yeah, Jesse from Fiji. All right. Well, so glad to see your enthusiasm today, guys. Well, I don't want to steal much of your time. I know you guys are super tired of seeing my face, and I'm going to leave you now with our super cool guest, who, by the way, I don't know if you guys have heard of this cute word called Potterhead, but he's a crazy huge fan of Harry Potter. If there are there any Harry Potter fans in here? I only watched three movies, but after talking to him about Harry Potter, I had to finish all of them. He makes it contagious, man. Well, without yeah, Jesse, you are. Without any further ado, I'm gonna be in the background helping Harshit with the questions that you have. Remember, please to write them on Slido, the widget that you have there below the chat, to keep the questions organized for him. Okay. Well, see you in a while, and I hope that you enjoy it. The stage is yours, Harshit. Go ahead.
Awesome. Thank you so much, Lewis. Thank you so much, Jesse, for the opportunity. Thank you, everyone, for coming and joining this meeting. Really excited to discuss a topic very close to my heart. When I first heard about AI, I wanted to understand what's all basically generative AI. I was a very engineer of 2010s. I come from the ML data analytics, doing all those machine learning algorithms background. So I was pretty, what is generative AI and how are we training the models on the generative AI? So I have been, trying to explain generative AI and how it really understands what we really mean to my parents, to my family, to my friends who are not in tech as well. So I thought this might be a good topic to, uh, to not to go into deep tech, but keep it high level. Explain how is all of this happening behind the scenes, so that you have an idea what are you interacting with, and you have your basics known in that sense. As Louis mentioned, we have a Slido open. Please put in any questions that you have. I will be stopping after each section, taking some questions. As I mentioned, it's a very high level presentation. There is always like a deep dive. There's so much deep dive you can do in AI these days. But if you have any question, you would like to discuss something, you would like me to like talk about that a little, I can do that as well. And this is like my I'm not officially working as a data scientist or an AI engineer anywhere. I love developers. I love what developers are doing, and it is my curiosity that I keep learning these things, and I'm just bringing. So I'll try and explain all the questions and answers in best of my knowledge. If not, the web's out there. I'm sure you all can explore more, but you will get cues where to go and what search what as you go through the webinar. Awesome. I'll jump into introducing myself a little. As I'm Harshit, I work as a developer relations manager for an insurance tech company called Guidewire. I was working at MongoDB previously, which is a document database company. And before that, I used to work at Topcoder, where I actually worked with Jesse Lewis. If you can see the photos on the right hand side, they are the photos of the past. Probably 5 7 years ago, and we used to have a really good time working together. So I was able to lobby myself and get a session slot for this one because I worked with these two. So it was easy for me to get a session slot. So thank you Jesse, thank you Lewis for giving me the opportunity to do this. I live in Dublin. I've lived in Singapore, and I'm originally from India. And I love butter chicken. It is not mentioned here, but I love butter chicken. I've had it with Lewis. I've had it with Jesse. We also run a small butter chicken squad and share butter chicken photos with each other. So it's very important to us. Butter chicken is one of I think has the most proportion in our bloods these days. So if you love butter chicken, feel free to ping us on LinkedIn or anywhere, and we can discuss the best butter chickens and recipes around the world. So awesome. Uh, all right. This is the agenda for today. I already see some questions coming up, so that's really good. I think when we are close to uh, those topics, I'll ask Louis to help me bring those questions up, and we can help out answer those as well. But this is the agenda for today. We'll discuss the evolution of intelligent apps. I'm sure if you have been in the industry, you would have heard about machine learning algorithms, recommendation systems, uh, you know, neural networks, and a lot more things back in the day. And then we'll see how all of that has evolved over the years to where we are in the world of generative AI. Then we will segue quickly into what are LLMs and how do they know everything? How are they, tracking? How do they have all the info? How do they answer us what we really ask them to? We'll see what is happening under the hood. Then we'll quickly, segue into something like search. So we'll try and see how currently the search ecosystem works. I'm sure you all have probably been using Perplexity or Chat GPTs to ask questions, and they return you the right things. We'll see how traditional search used to work, and then how the searching in these platforms is actually happening, and then how you could actually search something from your own data set, which is the core concept of building chatbots. So we'll just touch base these concepts, and then quickly in the end spend like 5 7 minutes discussing the RAG architecture and AI agents. This if you're new to AI, if and if you're not from technical domain, I'll quickly explain how they work. But if you want to explore more in these side RAG and AI agents, of course there's a lot more content available on the internet these days. Awesome. Let me deep dive into the evolution of intelligent apps, and we'll see how this has evolved. So it all kind of started with analytics. There was a lot of data. Databases were holding a lot of data, and that's when the first form of intelligence was actually doing some analytics. Uh, People used to go into the databases, run some SQL queries, try and find out what's happening. Or if you're using Excel, or if you're using Google Sheets, you are trying to analyze some data, and you're trying to see some correlation or some trends. That was the first form of looking into the data and looking into the intelligence that data could offer to us. Then from analytics, we jumped into called something like a batch AI ecosystem. When I say batch AI, this is basically you are training a model on a large data set, and then you are making predictions for the future. So, for example, let's say there's a lot of weather data. So you are training a model on the weather data, and then you are trying to predict what's going to happen in the next few years or few months based on how the trend has been. And this could also, that's just one example. There could be more examples like For example, you have data of a grocery store, and you try and you try and train the model on that data, and then you see what are the items that I'm going to sell the most in the next 10 years. So there's a lot of prediction heuristics to be done for the future. That is called batch AI. That was the era of probably I should say 2005 to 2010, 11, 12, the big era of everybody started doing batch AI. Machine learning models became a lot more prevalent, and training of the models was happening and during those days. From batch AI, we jumped into something called a real time AI. For example, you would have seen, if you go to Amazon.com and you search something, it starts possibly showing you the things in the similar in the similar range or similar profile. That's basically you are training the model on the fly based on your input, and then Amazon kind of brings in recommendations or predictions for you to look at what's going to happen next, or what you would pick from the profile. So that's basically something called a real time AI infra. And if I give you one more example of that, that would probably be again from a grocery store example. If you are probably ordering some stuff from online, uh, maybe they have seen some trend that whosoever buys milk also buys bread from the application. So basically, if you add milk to your cart, the model would run and they will start showing back, showing you bread as well as an alternative next option that you could buy. So that is called real time AI. There's a lot happening in this space still. There's a lot of evolution still going on. Uh, I was in New York a few years back. I was actually able to see an advertisement board which read some data from my phone or from my network, and when I cross it, it shows me exactly the advertisement I would want to see. Uh, so that's some of the things that we see AI bringing us in front of us, and that's only the consumer side. There's a lot more happening on that side, from manufacturing, industry, insurance, finance. AI is everywhere. Awesome. And then after this, after the real time AI came generative AI, which is something, which is like you are now generating, which is something we are using on all the LLMs, where you see them, where you see an AI chatbot kind of an interface, and you can ask a question. It is trained on large amounts of data, and it is able to generate a response one by one. So that's how we came to generative AI. Coming to like how did this happen? We were back in batch AI and real time AI. We were probably just training the models. We were predicting something. We were we had different algorithms to classify some data sets, predict where would this kind of a object lie. But how is it happening in generative AI? When it comes to generating AI, it all changed in 2017. Google actually revolutionized text generation. Google introduced something called a transformer, which is something they had a paper called "Attention is All You Need," and in that paper they defined something called transformer, which actually became the state of the art to approach the NLP problems. So back in the day when you were training some models for batch AI or real time AI, you were listening to each or training something on one uh, let's say one particular data set or profile, and then you would go and train on others. But transformer actually changed the way it worked, and it allowed to train uh, the data set on multiple things all at once. So for example, let's say we are sitting in a classroom, and all the students are actually speaking. If I was in traditional AI way of learning about what is everybody speaking, I would listen to each of them once and then absorb the whole text of what they're saying all at once. But when a transformer came, the idea changed to let's absorb what everybody's saying all at once. So transformer helped do that. And OpenAI's GPT is nothing but a generative pre-trained transformer. So it's basically a form of transformer which is going to, which is pre-trained and will generate responses out of that. And then this is the paper that you can take a look. It's attention is all you need. There are lot of many YouTube videos on that, how it changed the way data is absorbed and how the attention is brought into. So there's a feature here which is called attention. How is that brought into generating the right responses, generating the right things after you have your prompt in there. This is the transformer model architecture. I won't go deep into this because we want to keep it very high level for this session. So you can take a look at this paper. Lot many, as I mentioned, lot many YouTube explanations as well in there. All right. What are transformers? I'll kind of like quickly dive into this because this is important for how we build the next few slides and explain you to how it all comes together. So when it's a GPT or generative transformer, so generative is basically, as it says, is kind of deep learning. It's a model for understanding and then generating text or images or videos, or there are many things happening out there at the moment. And transformers are something like they analyze chunks of data called tokens. If you have been exploring AI, you know what generative AI, you know what tokens are. But I'll talk about those as well in a bit. But transformers are something, they analyze chunks of tokens, and then they predict the next token. So when we say generative AI, it is actually using a transformer to assess a token that you, let's say a prompt or something that you provide, and then they are trying to predict the next token in a sequence, and what they're predicting is based on the previous and the following tokens as well. So for example, you know, and all this tokens and all the data around the world is something that actually trained Chat GPT as a model as well. So Chat GPT was trained on over 300 billion words, and using those words through transformers, when you put your prompt, it is able to predict what the next word would be. So when I say generative, it's actually predicting what the next word would be, and that's how it works. For example, uh, let's see how it actually all comes together. So each word to be trained is transformed into a vector. So, for example, you have something like in the photograph down by the river bank. Uh, let's say we take the word by. By is actually transformed into a numerical vector, and the numbers in those vectors are actually capturing the relationship between the and similarities between each word. So, the first plus 5.8 might be capturing the relationship with the word down uh, and the word the in the next one, or maybe capturing a relationship about a few words before that and a few words after it. So that vector representation actually uh, helps us identify the relation between the words, and then these vector relationships are help us to plot these words in a multi-dimensional space. So vector is nothing but a multi-dimensional array of numbers, which where each of the numbers represent a dimensional space. And once they are plotted in the space, the scores on the pointers are actually closer to the ones they are related to. So for example, if I'm plotting these vectors, if I'm plotting like chicken and dog in the space, they will be closer because their vector or numerical representation might be close to an animal, and all the animals are probably closely related, so they are given the similar vector pointers in that dimensional space, so they're all plotted closer. Similarly, apple, banana, and apple, like apple of the company Apple, and even they all would be plotted closer, where the vector numbers are close to the fruits. Uh, and then these relationships are used to predict the next word. So, for example, if you are trying to, write something like, uh, uh, m- my current state of life is just, or let's say it's raining cats, and if you say something like that to the prompt, it's raining cats, and it will actually go and look for the words nearby, from all the data, from all the textual data that it was trained with, it will look and see and predict the next word. So it's raining cats, and it will go and look at the nearby pointers and say dogs, because most of the data that the GPT or any other model was trained with included dogs in there. Uh, I know. I mean, this is a little complex. This part is a little complex, how these are trained and how the vectors work. We will go and understand this very simply as well, and you will get an idea. Uh, so I'll touch base how how this all comes together eventually. But this was high level transformer architecture that helped analyze chunks of tokens, and then add and make it a vector, so that these all could be plotted in space, and the next word could be predicted. So similar vector, as I mentioned, similar vectors plotted in the space will be one another. So uh, a man and a woman will be plotted next to each other in that space, and they might have different vector representation. Each of these vector numbers might point out to some feature of that. For example, the 0.765 might be pointing out to legs. Like the man and woman, they both have two legs. So if you see, both of their representation are the vector numbers 0.765 and 0.774 are close to each other. There might be another vector number in there which might talk about the hair length, and man would be very far away from a woman's hair length. So in that case, you will see that these vectors are, the next vector might be very far, and that's what distances them. But yeah, this is how the vectors are plotted. We'll touch base them a little bit, and you'll get more idea as we proceed. But let's get into how LLMs work, and how, as I mentioned, how the next word is predicted. So now Chat GPT, for example, has taken in all the data uh, all over the world. They were, like, as I mentioned, like, they were trained on over 300 billion words. All that word has been, we've done the training, and now we input something to Chat GPT. Chat GPT converted all the words into vectors, uh, plotted them into a vector space. And now when we ask something to Chat GPT, for example, it is nothing but Chat GPT is predicting the next word. And how do they predict the next word? They look at the vectors, they look at the plotted words nearby, and they bring that as an answer. So if you search Chat GPT with, say, the car is, it will go and find out red as an answer and give red to you. Then, let's say you had a bigger prompt over something, it will take red as an, among itself, the car is red, and then try and search for the next word. So the why it is called generative, because it is always predicting the next word. It's not like it understands you particularly and then goes and finds something. It reads the prompt, it understands, it kind of like goes into the vector space, finds if something similar was said or done in the past, and then tries to predict the next word. So looks in the vector space, tries to predict the next word, and go from there. So the car is red. Now it will go back and start asking the next word. Let's see this example, like, tell a story, full stop. What do you think is the next word going to be? Generally, with a tell a story, if we go into the vector space and find out, over billions of times the word tell a story was mentioned, and after the full stop it started with something called once. So it will definitely bring in once as a word and put that in your chat answer. Then it will take in again, tell a story, full stop, once, and you know what the next word would be. It will take this as an input and try and get us upon as an output, because that's generally the word that comes, in all the billions of texts around the world. Once upon, what the next word would be. It will be a time, or a next token would be. So that's how LLMs generate. That's how LLMs were trained through the transformer model, and then they start generating responses over that. Now it is not always a word by word thing. It is, sometimes they look at different set of words. Sometimes the LLMs would look at once upon a time as one token or two tokens, and then try and predict what the next word would be. So, for example, when you write something called write a story dot, it is tokenized into write a story and full stop. It is embedded into the vector space. This is where this is probably a two-dimensional vector space, but imagine it's a multi-dimensional. It is embedded into vector. The vector numbers are created, and then it is plotted into the vector space, an n-dimensional vector space, and based on that, it starts predicting the next word. So based on that, the whole transformer and the attention is all you need algorithm is run through it, which has a special feature called attention. I would suggest you to go and read about that. And it looks at which is the next word going to be in terms of the distance around these plotted vectors. And based on that, it predicts that once is the most preferred word, and then it becomes write a story full stop once, and that's how Chat GPT and LLM generates the response to you. Uh, Similarly, it goes into as mentioning, it's not only about the previous word. Like it's not just about write a story full stop, and it looks at story or dot to predict once. It is sometimes depending on different ways of predicting the data, different GPTs, and they are trained very differently. For example, there are like these 1 gram uh, training sets where they only look at the previous word, so only one word, and then they predict the next word. So if this was the data set, they will look at this and say, hello, how are, and they'll see happy is the next word two times, and all the others are one time. So happy is the next word. This is like a 1 gram prediction system. When it comes to 3 grams, it looks at hello, how are, and then tries and see among these three words which is the next predictable word, and then prints the next word out there. Similarly, it doesn't end here in 1 or 3 grams. There are different, there are n gram word as well. It scales to a lot of big number. That is why Chat GPT and all the AI algorithms and models are very efficient in actually knowing what you exactly are looking for, because they they're trained on different grams, and multiple heavy grams as well. So it says, hello, today I would like to inform you that slash, and the next word in the data set is the. So it will go and print the. Then it picks up the text with the, takes it back to the vector space, looks for the nearest word, and then brings the next word. So that's how LLMs are nothing but they are only predicting the next word, and that's how they, through the billions of text and data they are trained with. And the innovation actually happened because it used to take long to train a model on a particular thing. For example, if I was building a image recognition model, and I was, making my model train that this is one, one finger is one, two finger is two, three fingers three, and doing some hand gesture training, I would have to train my model on my hand images or multiple hands images for years, for not years, but let's say a few months, to actually train them and then being able to predict what am I saying. Am I saying one through my hand gesture or two? But now it's become much easier because through that attention is all you need, and the transformer model uh, paper, a lot could be trained all at once, and the predictions are happening based on all the trainings, all the data available around the world. I'll I'll um I'll just explain this a little bit more. Transformers, the concepts, what we studied, but I'll stop here for a while. If you have any questions, we can bring them up, and then keep going ahead to touch base more about the search as well. So transformers in general is, as I mentioned, when you put a word, it is when all the data that you have is converted to numerical vectors. They are positionally encoded in a vector space, and they capture the order of the words. And then there are these self-attention layers highlighting relationship between these words, based on how they are, how they are in the available data set. And through a feed-forward neural network, you can go and study more about neural networks if you are from the tech background. And there is like meaningful patterns that come out. And then you are, based on the question that based on what prompt we give to the generative AI, it is able to predict the next word, and then it picks up the next word and the prompt and predict the next word and the prompt and predict the next word. So generative AI is nothing but predicting the next word. That's how it works. Awesome. I'll pause here, Louis, if there are any questions. That Yeah.
Yeah, definitely. We have a bunch of questions arriving, both from the chat and from Slido. I will start with Slido. We have Isa. She's asking, how does natural language processing enable AI systems to accurately capture the nuances of human language and intent beyond just keywords?
As I was mentioning, it is all about training. There is a lot of natural language text, videos, images available online. Uh, AI, as I mentioned, generative AI is nothing but it goes and looks back into that text through these models, through this transformer model, and then tries and predict the next. So AI is being efficient because there is a lot of data already available online that that the models have ingested and learned from. So yeah, that's why it is able to capture the nuances. Let's say you only have a model that works on some particular use case. Let's say only on the grocery data set. Then if you ask them something like, where should I go for a vacation in the next month because I feel like going to a place near the beach, it won't be able to answer because it only has the grocery data set. But because of the transformer model, a model like chat gpt is able to ingest so much data that it looks into all of that and then brings you what has been the most tries to look tries to match you and correlate your prompt to something that has already happened in the world and then generate the answer. Yeah.
Okay, thank you. Thank you, Harshit. We have another one from Isa. She asks, can you explain the role of context and inference in AI's ability to understand the underlying meaning behind user queries or statements?
I'll come to this one, Louis, after this a little, so you'll get more idea about the context and inference. Yeah, yeah.
Okay. Okay, cool. And what are some of the common challenges or limitations that AI systems face in understanding human language, and how are these being addressed through ongoing research and development?
That's that's a very interesting question. I know we only have 1 hour, but there could be another topic of conversation around it. That the hallucinations and
Mm.
the private data that you want GPT to access and give you answers. And there's a lot going on in this field in terms of research as well. How do you store the vectors? Vectors are huge. They take a lot of data space. And how do you search through the vectors? How are LLMs doing that? All this requires some research and development. So I'll not go deep into it, but this is a space I hope Lewis and Jesse bring me back for another webinar and I'll talk about this.
Awesome. Also, a webinar about Harry Potter. People are already asking for it.
Yeah.
Okay. Well, we have Kasia asking about context. We'll reserve that for what you have to say
Yeah.
right now. We want to reserve it. And also, yeah, context and inference. We have
Mhm.
Gabriela. How does the model learn the relationships and similarities between words during training?
This is exactly what I was mentioning, Gabriela. Like the transformer model, it looks at the existing words around the world. If you see that the king and a man are always mentioned together, they have similar features, they are spoken with the nearby same similar words, they end up together in the vector space. And I'll talk about how these vector embeddings work in a bit as well, so you'll get some idea how are these similarities inferred. But it's basically where that if you start writing, let's say 300 billion times your name with something like intelligent, your Gabriella will always occur close to intelligent in GPT models as well. So it's exactly that. When we saw the models returning wrong information, it was because somebody had written the wrong information somewhere, billion times.
Mm.
That's how they detect the relationship between words and training. Yeah, and all of this is through those vectors. And if you read the paper, or any attention is all you need. There's a lot good info of how they are inferring these words. Yeah.
Well, okay. We have three more in Slido. We have Irene asking, "Hi Harshit, please give us a brief overview about how to create an adequate AI prompt using for instance ChatGPT 5."
That's also a prompting is again. I think what I've showed, like it's the next word prediction. You will get an idea uh, how to best prompt your models. But prompting is another, prompt engineering is another, uh, uh, another webinar in itself. As I was mentioning, AI, there is no end to discussing various directions at the moment.
Yeah.
But yeah, this is kind of out of this scope of today's conversation. But yeah, understand the basics, and then you will start evolving your mind in terms of how the prompting should be done in the best way. Yeah.
Okay. Well, we have Nuri. Hi Harshit. How to maintain user data privacy in conversational AI systems that continuously learn from interactions?
I will, Nuri, I'll touch base RAG in the end of this presentation, and you will get an idea of how data privacy is maintained and how private data is shared in a conversational AI system. Yeah.
Yeah, yeah, and then, yeah. Remember you mentioned like when the questions about common challenges, this was something that came out of your mind quickly, like ethics, data privacy, and
Yeah.
hallucination. And finally, we have Hira. When AI interprets our hidden intent, how are privacy and transparency issues handled? I think it's probably related.
Uh, when AI interprets hidden content, how are praise and transformation? That's again, a question that is dependent on, the outside of the scope of what I'm trying to discuss today. But this is basically our data, which is public on the apps, our public pages. It's kind of depicting from that. There's a lot of controversies around how does AI know about XYZ people and things around the world. Still an area to be researched, but yeah, I'll we'll keep the talk focused to discussing, how is all of this happening, and how does the vectors and all come together to get you the right responses. So yeah, yeah.
Uh, okay, those are all the questions from Slido, Harshit. If you want to go on, you can continue now.
Awesome, awesome. Yeah, I think some of the questions in there you'll get some more idea, and then if there are some interesting topics as you mentioned, the privacy and transparency, as well as there's interesting question about the the limitations and understanding the hallucinations and those details. Not in this scope, but yes, you can always reach out to me on LinkedIn. I have some good places to look up to, and I can share those links, and you can learn more about these as you go ahead. Yeah. Awesome. I'll jump into traditional search and matching words, which is will give a lot of answers in terms of how the private data is accessed, and how do we build a conversational private chatbot kind of an ecosystem, and we'll touch base that.
All right.
Yeah. So back in the day, I think you all have been searching, online on Google, and the way search works is an interesting concept. Google changed a lot of these things, page ranking algorithms and such. But the easiest way to search for something, if you have to search, let's say you have to search for pasta, you would go one by one, searching for the letter P. If you find P, you will stop and look for A. If you don't find S after that, you will stop. You will keep going and then again start searching for P. That's the most, this is like, uh, this will like blow your computer if you start searching in billions of data. So search, it traditionally used to happen like this. Then came something like called index search, for example, in which, if you have seen your books, there's a back page which has indexes. It kind of shows where each word is mentioned. If you have seen, like, you know if you read books like yellow pages or something like that, you can go at the back, you can see where this word is mentioned, and then go back to that word. In various books around the world, it is the case. Similarly, search became like an index thing. If you were searching in your data, you would actually originally convert your text and transform and remove something like, words like with. You will remove filler words. You will do some stemming, and then you will improve the casing, like make it all equal case. And then based on that equal case, you will create an index. You will say that the word lamb is mentioned in the page number 2. You will say the chicken is mentioned on page number 1 and 3. So that was the next form of search. You would index the data. You would like kind of then look into uh, finding that where this word exists. So similarly, like if you have to search for pasta, it will go to the index, search in the index that this exists on this particular word, and then quickly find that field or word or page that you're looking to find. So that's how the search basically used to work. And now we are seeing something like shift to something like semantic search. For example, if you have seen Airbnb website, it has a very fixed bar where it tells you where do you want to go, and then asks you a few options in terms of, do you want a beach view house, do you want a lakeside house or a lakeside homestay. It doesn't allow you to search something like, I want a place where I could see horses running out in the window from my window of the house, and all those things. You can't search that, and that's where generative AI and these this transformer model or the embedding ecosystems help us do that thing. So, for example, I recently had Airbnb data set which I trained on a particular model. Sorry, I actually like embedded all the reviews and descriptions of that particular Airbnb data set, and then I was able to ask that data set in the way we asked Chat GPT around. Can you tell me a place where I could see horses running outside the window and all those things? And I was able to exactly find out that this is the place that you could go. So we all are now moving to doing more semantic searches than doing keyword based searches in the ecosystem. So that's where we are these days. And the way it works is semantic search works with vectors. So, and as you know, there are some questions in the chat that I saw, uh, that that what are vectors and what are embedding vectors, what are the private data info and all those things. We'll clarify that in this section now. So I'm sure you all know vectors, but I'll touch base a little on this. Vectors are simple. For example, if you have to identify where is this shower head in this big store, I would use a vector like aisle and bin to identify where this is. If I have to identify where are the long handle shower with pipes available, I would, use a vector aisle, bin, comma, uh, rack number, comma, let's say pipe length or brand or anything in the vector. So vector can grow. So each number in the vector represents a feature of that particular text or product or whatever you're doing. So that's a vector. Vectors also exist in GPS coordinates that they help us predict exactly where you are right now. At it could be long and latitude, so that could be a smaller vector. If you want a more featured vector, that could be long latitude and altitude. You could do that in the GPS coordinate space. Similarly, when you're playing a game, it could be, we are all in a, we either play 2D games, which are like Angry Bird, or sometimes we play 3D games which are more like Minecraft, where you could also move in depth and or throw or do things in depth as well. So if you see vectors, with each vector we add, with each dimension we add in the vector, we are adding a feature. We're adding a feature that represents that particular uh, you know uh, information about that particular word or feature or object. So as I mentioned, you could go from one dimension to n dimensions. There could be many dimensions. Uh, all the embedding models, or OpenAI has embedding models, Gemini has embedding models. All these models you see, they have a set of vector size that basically represents how rich they are in terms of storing the features of that particular object. So, for example, if you want to store something like a man, you could store either something like three things like short hair, uh, and a few more things about features about the man. But if you want to store a lot of things, they wear shirts, they wear pants a lot, they wear suits, all these things. This is about their clothing. You could actually do a lot more things in that vector space. So there are some embedding models which embed words into 3 or 4 dimensions. Some would do 1400 dimensions. There are models which are doing now 4096 dimensions of a vector. So each word is converted into 4096 different features that that word could have. So, for example, if you have something like a quick brown fox, the first vector might represent something related to quick. A second vector might relate to something, to brown, and the third dimension could relate to something like an animal that can fly. So if you see, we have a vector number that is represented in negative. It might be far away from, because fox don't fly, so it might be something like, it's a quick brown fox. In terms of flying feature set, this numerical number represents the flying ability that is not anywhere near the other animals or birds that fly. So this way, a quick brown fox or a quick brown eagle would be far from each other in the flying dimension, and that's how the vectors are represented. Then these vectors are, as I mentioned, there are embedding models by OpenAI and all these generic model providers out there. They have these encoders, and they convert the text or the object you mentioned into vector. So, and it could be text, it could be image, it could be video, it could be code or anything. There are different models that they run through, and then they convert these data into vectors. Once we have these vectors, as I was mentioning earlier, they are plotted in the space, and then we can look at the nearest similar words, or do the semantic search or similar search to find out what exists out there. So, similar vectors are plotted in space will be one of the, for example, man and woman would be near to one another. Uh, and based on what you are searching and how you are searching, it might return man and king as closer to each other. And based on the embedding models you use, it might return woman and queen, uh, in man and woman, and woman and queen in one set. Or some of the embedding models might return man and woman close to each other, and king and queen close to each other, rather than doing man and king. So all of that depends on, there are various embedding models, there are various algorithms they follow in terms of embedding. They have different dimensions, so it all depends on those, how they return the similarity between these words. All right. And then as I mentioned, there's a nearest neighbor algorithm, KNN algorithm. We call it K nearest neighbor algorithm, that helps predict the similar vectors, like finding king is found close to man. So if you're looking for a similar word to king, you will get man out of that. In some embedding model, or in some you might get a queen as well. Awesome. So basically, vector search is the concept. So that allows us to find the relevant results. So what really happens is, if you have this type of vector embedding model, and you search for something like, give me something similar to, uh, let's say, a tiger, right? So tiger is then converted, whatever you query, whatever you search is converted into a vector, and then also embedded into this vector space. So you search for tiger, tiger is converted into vectors, tiger would be put as a dot somewhere here. And then based on the k nearest neighbor algorithm, the vector starts finding the nearest dot, or the nearest point, plotted word out there, or n-gram word out there. For example, with tiger, it might be close to cat, and if you search something, something like tigers, it will start returning you, similar to tiger, it will return you cat, because it will plot tiger close to it, because they have similar features. So that's how vector search works. You have your data plotted in a vector space, you find something close to it, you look for the nearest neighbors and find out the data. So yeah. uh, and as I was mentioning, you have your data, you put it into a model, it is vectorized. Similarly, you search for tiger, it is put into a model, embedded, and then you search for nearest neighbors, and you find the similar results. That's how similarity search works. Now, vector search empowers a lot of use cases. One of them is RAG. We'll talk about it. There is semantic search, as I was mentioning, the Airbnb type of a search. You put all the Airbnb description reviews into embedding model. You store the vectors, and then you can do a search of something that ends up similar to what you are asking. That's all comes into semantic search. Then there are other as well. There's similarity, recommendation engines, anomaly detection, and image and audio media search. One of the interesting use cases I always mention is there is a car company in Europe, and they are kind of uh, they are listening to engine sounds. They have embedded all the engine sounds data of the past they had. They've converted those to vectors. So now, whenever a new car comes in for service, they listen to the engine sound. They plot that into a vector in the vector space. They look for the nearest vector and they find out what the problem could be in the engine. So that all is happening because of the vector search, the way the embedding models help us vectorize the data, and then we're able to find the similar solutions. So that's a pretty interesting and exciting example that happens over there. Yeah. I know we have 5 minutes left. I got a warning from Lewis, but I'll quickly rush through the rest of the parts. Coming to, I hope you all got how vectors work together. But coming to how all this happens, how the vector search along with your private data helps build those conversational bots, and all the bots you see on various websites. How does that happen? So, and that concept is done through RAG. RAG is nothing but it's called retrieval augmented generation. It's a complex word if you're not in tech, but just don't go into that. The idea is to uh, enhance the quality of a pre-trained LLM model, which is already pre-trained, but use the information from our own external sources. Let's say you give your insurance policy to uh, how tell me something about my insurance policy. LLM might not know about it, but this RAG architecture allows that to happen, and we'll see how it works. So to explain RAG, I'll just jump from one by one from simple prompting to RAG to others. Uh, you all do simple prompting. You all ask questions to GPT LLMs. You put a prompt. You ask, uh, you know, how can you, let's say for example, can you convert this my English sentence to Spanish? They will take it. They look for similar Spanish words in the vector space, generate an answer, and give me the answer. Now, when it comes to private knowledge, let's say I build my own language where something is known as something, and LLMs don't know about it. They don't have that knowledge. They cannot handle complex tasks. They will just take a prompt. They'll generate the next word to next word to next word and give me an answer. There is no personalization. It hasn't looked into my areas of what I like, what I don't like, and I might have to put that in my prompt as a context, and then go about that. But that's how it works. It cannot self-revise, based on what output comes out. It cannot refine responses. That's the limitations of a simple prompting that we all do on Chat GPT these days, or Gemini, or Claude. The retrieval augmented generation is a method to actually bring a knowledge base to the as a context to the LLM. So remember how we were vectorizing the data, and how I was vectorizing the Airbnb data set. Anything you have about your own product, let's say we have a Populii documentation, we will convert that into vector. Whenever somebody asks a prompt, we will put that, find the similar vectors around it, and then attach that as a context to the LLM, and then the answer is returned. So this is the way how all the chatbots you see these days are working. They are actually, so they have access to the right info through this architecture called RAG. You can go and read more about it, and they can provide personalized responses out of that. They still cannot handle complex self-revise and complex tasks, and cannot self-revise and responses, because that's how they are architected. But the next evolution to RAG is now the agents, which has the ability to do some reasoning, look at the memory, call some tools, and then that allows them to handle complex tasks and also self-revise and refine responses. Uh, I'm not going to deep dive into all of this. Just explain a RAG. I know we are over time, but quickly do a explanation of RAG example, and then uh, we can take any questions, or you can always reach out to me on LinkedIn, and I can answer those questions as well. Uh, we'll see when to RAG and not to RAG real quickly. For example, if you have something like "Hello, how are you?" we don't need to do a RAG architecture. If you are something like "What is a travel reimbursement policy for our organization?" Yes, because you will have to provide them with the travel reimbursement policy. Uh, what are some recent movies that I might like to watch? There is personalization, uh, because it wants your data. You have to RAG. You have to provide the recent movies you watched in context, and then the RAG, the architecture will work on that. Uh, it's something like create a virtual travel assistant that can help me with the vacation planning, including making bookings. This is not RAG. You need agents for that. You don't need any personal info attached to it. It is going to be your travel assistant who will help you do the bookings. So you have to take your call and understanding what architecture you want to take when you are building your application, and then use that. Uh, I will skip this and come to a quick example as my last thing. Uh, now imagine if I ask an LLM, I'm looking for a recent movie with a bit of action, some sci-fi, a happy ending, and kung fu. Can you give me some options? The LLM would say, sure, I can give you anything recent because my knowledge is cut off at 2021, but I would be happy to recommend Kung Fu Hustle. It has some action, fantasy, blah, 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 and all those things. Uh, when it comes to doing this with RAG, let's say I have an IMDb data set with all the reviews, all the details available. I will vectorize my IMDb data set. My client will ask the prompt, similar prompt. I want to XYZ movie. It will run a semantic search, the same vectorized semantic search on the data set. It will return the contextual data of a similar, words or movies around it. And then using that, we'll go to the LLM, and then the answer that will come will be a very enriched answer. For example, the embedding of Lord of the Rings would result in something like these kind of words, the Fellowship of the Ring, an ancient ring thought for lost for centuries, while Frodo and Sam continue that, this and that. And that's how the result will come. A similar movie embedding would return something like, some in this form, or this detail. And now when I ask my question to it, it will pick up using the embeddings I have. It will go into the vector space, search for similar vectors, and bring back the answers. So when I ask now with the retrieval augmented generation architecture with my IMDb data set vectorize and attach, it will return me, sure, based on the movie database I have access to, it looks like everything everywhere all at once has everything you're looking for, this and that. So RAG, this is how chatbots in various ecosystems are able to answer you from their own data set, uh, because they are able to attach the semantic search, the vector info as a context to the prompt that goes to the LLM in this case. So yeah, I think I'll stop here, Lewis. We are 3 minutes over, and give back to you. Can we take any questions, Lewis, or we are?
Yeah, I think yeah, we can take one of the questions that we have pending. Fortunately, we can't take them all, but it was something rather curious. It is Kamal asks, can we make AI with feelings? It's a big question for now. At the current level of AI, everything seems possible.
Yeah, that's, I think, Kamal, if you start searching for models, there are a lot of models that are only getting trained on emotions and, emotionality. Then they also have some pre-trained context that goes into them, to try and understand the emotions really well. So so it's all about training. It's all about what data you train on, how do you configure the number of vector features, and all that, could be possible based on how we tune it. It's just a system that is reading the previous data, previous info, and then trying to predict the next thing. So what you train on is all that matters to bring more feelings to it. Yeah.
Yeah, awesome. Yeah, and the other ones, I didn't want to go through them because basically I think you covered them with the context explanation and the semantic search fundamentals. Well, that's it, man. This was so illustrating. There were many things because we typically interact with these tools these days, and we have no clue what's happening behind the scenes, you know. And now when you see the whole process of, decoding what you say, putting them into vectors, and then making calculations and approximations based on, nearest possible match. This is super awesome, and I really love the transformer analogy with the with the actual transformer. I predicted the words. Yeah, I think it was very educational, Harshit. Thank you so much. Well, it's very sad to say goodbye to this series overall. We had 9, 10 episodes learning many things. The hardest topic was AI, and I'm super happy to have you today, Harshit, to close it. And thank you all the audience for joining. We love seeing your comments and your enthusiasm. Thank you once again for being here. And Harshit, the stage is all yours to say goodbye.
Yes, thank you everyone for spending the last 1 hour with me. As I mentioned in the beginning, I'm trying to bring whatever I learn to the community and help the community with whatever I could. If you have any questions, if you'd like to discuss something interesting, look for best of resources to look into. I'll also learn from that because when you bring a question to me, I go and research for the right answer and make sure the right info comes to you. I'll just put my LinkedIn in the chat. Feel free to reach out anytime, and I'll be able to help with anything that is needed. Yeah. Thank you, Lewis and Jesse, for the opportunity. Thank you, Populi, for running this webinar series. And I think it's been great for the community.
That's awesome, man. Thank you so much, Harshit. And goodbye, everyone. Have a great rest of your day and evening. Bye bye.
Thank you, everyone.